Yes, I think so. 6p.
Colors. How many colors is there?
Or we could just
Four.
follow
Four
the
colors.
chart left to right and just like
Yeah, and this is the
No,
exact
there's
same
five.
order as
There's
when you
six.
go through the periodic table.
Wait,
There's
that's red
six.
and then
There are
pink,
six.
right?
There are six.
Green.
There's six.
That's red.
I looked at red and said green. Red, green, blue. This is like a burgundy color, and then pink,
And then black for
and then black.
six. For six.
6 different colors. Come on, Jennifer, we don't have all day.
But I'll take a picture of it.
Take a picture.
I wrote it after 5.
Well, 5 starts with F.
So. We're gonna have to figure out.
This was $9.
Yeah, and you can number your periodic table, the rows on it. I always suggest you just number the rows on your periodic table, then you have it. It's pretty easy.
Intelligence, that's all she wrote was energy level diagram. Maybe that's
She didn't
why.
take the time for that, huh? Yeah. I showed it last hour, and I didn't enter yours, but I'll try to finish early enough to do that. I have 4 grades to enter, and it doesn't take that long. I'll try to get it done.
Relax.
No, you had a bad day.
10 more days. Well, I'm not. I don't have
Well,
enough
it's one of the
time.
high scorers. I don't know what they do if they take like top 10 or 20% and make them honorable mention. I don't know how they cut off the honorable mention. Is it fun? This is a way of arranging how the electrons go into atoms. This is not obviously a physical model, but it's an energy profile for the electrons and how they arrange themselves into an atom. 1s is the lowest energy. As you can see, my arrow's kind of wimpy, but it is going up. Energy is increasing as we go up. So 1s, closest to the nucleus, is the lowest energy, and then 2s is next. 2p is just a little bit higher in energy than 2s, and they go on like that. Do you remember what p means? When I say 2p, what does that p represent? The L value, the sublevel, right. And what number L does p go with?
1.
L equals 1. How many values are there for m sub L if L is 1? 2. No. 3. There's -1, 0, and +1. That's why the p's always have 3 lines next to them. S's only have 1 line next to them because L equals 0 for S's, and m sub L would have to be 0, and that's its only possibility when L is 0. What about when we have D's? That means L equals 2. How many possible values of m sub L are there?
2, 2.
Right, it goes from -2 to +2, which is -2, -1, 0, +1, and +2. That's why we have this certain number of lines next to each term. The lines give the possible orbitals. It's true. You know how the D's have those different shapes? There's 5 of them, though. And really, there are 5 what we call degenerate orbitals, which means even though they don't all look exactly the same, they all have the exact same energy. And because they have the same energy, when we're comparing the energy of these different things, they all go on the exact same amount of energy. So when you have P's, D's, and F's that have more than one possible line, we call those degenerate orbitals. It just means that they all have the same energy. And it doesn't really matter where the electron goes in any of these three. It's not like the one farthest left has less energy, so it gets the electron. Normally, we just start from the left and go to the right. But it doesn't really matter what orbital they're in. Okay, now just a couple of things about filling electrons and how it works. Let's take a small element like phosphorus. What would the arrangement of electrons look like in phosphorus? Well, phosphorus is atomic number 15, so that means we need 15 electrons in this model. Electrons always are closest to the nucleus as possible, so they always start with one s and then fill out. So the first 2 electrons would go in 1s. After 2 electrons are in 1s, it's full. That's all it has room for. So then move up to the next energy sublevel. In 2s, same thing. Put 2 electrons in there, and it's full. So we've taken care of 4 electrons. Into 2p now. You remember how we fill p's and d's and f's?
Go one by one.
Yes, put 1 into each before you make any pairs. Now, when we have s's, we don't have a choice. We only have one line there. It's going to go up and then down immediately. But for p's, you're going to do this. Up, up, up. Before any pairs are made, put 1 into each. This is not how we thought we should do it. This is what scientists observe about the behavior of atoms. Is they'll put 1 electron into all the orbitals before they pair in. So this is 7 electrons right now. There's 4 of them, and it's 5, 6, 7, 8, 9, 10. Once you have 1 in each, then go ahead and pair them up. 11 and 12 go right there. And then 13, 14, 15. This would be the electron arrangement for phosphorus. Now, is phosphorus stable this way? Is it hoping to be able to react with something? Whenever you see unpaired electrons are not stable. Electrons tend to get paired up in their orbitals. That's why phosphorus tends to gain 3 electrons and become negative 3. Because it's got 3 unpaired electrons right now. So when it gains 3, it will pair those 3 up. Yes, sir?
Does it matter if the arrows are up or down for the ones that are not paired?
Yes.
By convention, we'll always put the first electron facing up. So we all do it the same way. If half of us did them up and half of us did them down, if I did this, the implication is that electron became excited. This has a little bit higher energy than all 3 up. Because any change in the lowest possible energy is going to require energy to be put into it. So that would show an excited electron. Even though you say, well, no, there's no excited electron, the electron has to jump up higher. But this has changed. Something about this thing has changed. So in order to make a change, you have to put energy into it. So that's why we always put the first arrow up. Yeah?
How do something like violate the octet rule? Like, does it like to do that? Like DPL5?
Yeah. That's the next chapter. Thank you. Okay, let's move on. Now, this is another question that was taken out of the book. How many electrons would fit with these quantum numbers? How many electrons would these quantum numbers apply to? So, how many electrons can you have with the n value of 0, L of 0, and m sub L of 0? 0 was right. Why? What's the matter with this set of quantum numbers? If you can't have any
It
electrons?
doesn't exist.
That thing right there, you can't have an n value of 0. That would be inside the nucleus. Okay? So the first energy level is 1.
Wait, so the entire first will be like invalid?
Yes, it's invalid. Yep. How about the second row? N is 2, L is 1, m sub L is negative 1, and m sub S is negative 1/2. How many electrons would those 4 quantum numbers apply to? 1. That's something called the Pauli exclusion principle. Pauli is the last name of a guy, not the first name. Old. From the Rocky movies.
Yeah.
Right? Yeah. The Pauli exclusion principle says that there's no two electrons in an atom that have the same set of quantum numbers. That every electron is going to have a unique set of quantum numbers that only leads back to that one electron. So if you're given all 4 quantum numbers, that's good for, as long as it's a legitimate set of quantum numbers, it's 1 electron that'll have. Which electron is it? N equals 2 and L equals 1. That would be in 2p. -1 would be the first line on 2p, and down arrow for -1/2. So we're talking about this electron right there. That one. 2p, remember the m sub L values are -1, 0, and +1, so that's on the -1 line. Yeah.
Wait, so if it's positive 1/2 would be the up arrow?
Yep.
If it's negative 1/2
Right.
would be down arrow.
Yep. That would be +1/2. All 3 of the other numbers are the same.
Would we have to specify or just write 1 electron?
Yeah, no, just say how many electrons. That's what the question is. Give the maximum number of electrons in the end. Okay. Now the third line, it says how many electrons with an n value of 3 and a +1/2 spin exist? Huh?
9. So 5, 6.
N value of 3, +1/2 spin. I'm going to take you back here. In fact, I'm going to erase.
So we're just trying to see
5, 9,
maximum.
8.
So that's like
3, 4, 5, 6, 7, 8.
the highest value.
Yeah.
Biggest element. Yes.
What do you mean the highest value?
Like highest value of electrons. Maybe
Yes,
is it-
yeah, how many total electrons would have an n value of 3 and a spin of +1/2? Now, if you have an n value of 3, we're talking about 3s, 3p, and 3d. Yes?
It would be 3D. If you want the
No, we don't want just the highest, though. We need an n value of 3. So that could be that, or that.
Yeah.
And a +1/2 spin means in 3s, how many +1/2 electrons are there? Just 1. It's right there. In 3p, there's 3. In 3d, there's 5. Total of 9. Yeah, you were right.
Oh,
Hold
so
on.
you want the total number.
Yep. Right. Everybody okay with that? Elizabeth?
Yeah, I think so. I remember this from last year. So.
Okay, but you didn't quite catch something. N is 3. That means it's got to be one of the blue ones.
Yeah.
And they're all fine, and they all should be counted. And with a +1/2 spin, on that line, there's 1 electron that can have a positive spin. On these 3 lines, each of them can have 1 with a positive spin. And then there can be 5 with a positive spin in 3D. So 5 plus the 3 plus the 1 is 9. Okay. What about the 4th line? 2, 2. What about this would be 2D. No, there's no such thing as 2D. There's no 2D. Okay?
Only 3D.
And what about 1 and 0, 2, and +1/2? How many electrons would have that set of quantum numbers? Another 0. Because this is okay, this is 1s. But if we're in 1s, there's only one possible m sub L value, and that's 0.
What does M sub L mean?
These things. Like the Ds have 5 orbitals. There are 5 different arrangements where 2 electrons can be. Those are orbitals. Yep.
So how can orbital be negative?
Yeah, D means that L equals 2. So the m sub L values are -2, -1, 0, 1, and 2. Since these are all degenerate, it doesn't really matter which is which. It's just arbitrarily that I'm assigning this one to be -2. It could be this one is -2. It doesn't really make a
How
difference.
can it be negative?
Those numbers really don't have any mathematical purpose. They're just symbols that we use.
Oh, okay.
I mean, they all were a result of the Schrodinger wave equation.